Hello, this is the Unit 1 Module 2 video office hour. So these are questions or very similar questions that were covered during the office hours on Tuesday, Thursday, and Friday. A lot of different questions spanning Unit 1 Module 2. These are all questions that you would be expected to answer under time constraints. So we start off with we have two substances that have two different boiling points, A and B, one at 50 C, one at 75 C. And then the question is, at that pressure, wherever those boiling points were determined, what can be said about the mixture at 60 degrees C? Select all that are true, meaning that there's probably more than one answer that's true. All right, so let's construct the vapor pressure curve given this information. So we have substance A and substance B, and they have two different boiling points, and we're interested in this 60 degrees C region that lies between A and B. And so we use our diagram, right, that helps us out to determine what are the phases of A and B in the different regions. So above region A, above line A, we expect A liquid. Below line A, we expect to get A gas. Above line B, we expect B liquid. And below line B, we expect B gas. So 60 degrees C is between the two lines, which means we expect A gas and B's a liquid. Okay, so with this information analysis, we can now go in and start answering the individual questions. Question A says the mixture can be separated since A is a liquid and B is a gas. Well, that's not true. We just found the opposite is true. The average kinetic energy of both substances is the same. Absolutely true. These are at the same average temperature, 60 C, so they have the same average kinetic energy. The mixture can be separated since B is a liquid and A is a gas. Absolutely. The average kinetic energy of both substances could be the same if we knew the mass, and that's not true. The average kinetic energy just depends on temperature, so that would not be true. The average velocity is the same. That's absolutely not true. We need to know the mass. That makes F true and E false, right? If we knew the mass, then we could find out if the average velocity is the same, because kinetic energy is proportional to mass times velocity. If you know the mass, then you can determine the relative velocity. So if the masses were the same, they would have the same average velocities, and if they were different, then they would have different velocities. The potential energy of substance A is higher than that of B at 60 to C, and that is true because A is a gas, so it's going to have higher potential energy than substance B, which is a liquid at that temperature. So lots of great questions that can be asked given this information. Okay, so we have a pot of boiling water. It's allowed to cool. So let's make an image. So initially we have a pot of boiling water. So we have liquid particles and we have gas particles, and they're at the boiling temperature, which is hot. Our final state is room temperature, where pretty much we only have liquid particles. All right, so that's how we're going to evaluate the change in potential energy and kinetic energy. So the kinetic energy is definitely decreased since the temperature is decreased, right? So we know that the answers are either B or D. And the question is, going from gas to liquid, what is that change in potential energy? Well, that's got to decrease because we went from gas plus liquid, which is at a higher potential energy, to liquid, which is at a lower energy than gas plus liquid. So the right answer here would be B. All right, so here we have a vapor pressure curve, and we're asked to draw a Peck diagram consistent with this information. So the first thing we need to do is assign the potential energies of the liquids. And we do that by finding out what the boiling points are. So water has the lower boiling point at about 370, and it looks like C2CL4's boiling point is about 390. So we know now when we build our PEC diagram, well, first what we're going to do is we're going to put all the gases in the top right? So this is where the gases go. So the gases water, gases C2CL4. They have the same potential energy, same configurations, because for the most part the gases are identical. Gases will always have high potential energy and be very near zero. The reason why they have different boiling points is because the liquids have different potential energies. The kinetic energy is a measure of how far the potential energy of the gas is to the liquid. So if we have something that has a lower boiling point, it'll always be at the higher potential energy. Right? So this is a more stable liquid, C2CL4. It's got the highest boiling point, stronger interactions. Water is less stable because its boiling point, right? The difference in potential energy here between gas and liquid, which is measured by the boiling point, that difference is less than it is for C2CL4. So the main thing here is that both gases have high potential energy and high configurations. They're shown at almost the same place. And then the liquids are down at low configurations, low potential energy, but because they have different boiling points, they are shown with different potential energy liquids. The lower the boiling point, the higher up the potential energy is the liquid, and the less stable it is and the weaker its interactions. Alright, so this is the example we did in class. So from the vapor pressure curve, we made the PEC diagram in the previous problem. Now we have a PEC diagram, and we're going to ask to make the vapor pressure curve. So we look at this and we see, well, the boiling point of nitrogen definitely is less than the boiling point of oxygen because the liquid nitrogen is at a higher potential energy, less stable than the liquid oxygen is. So if we were going to draw the vapor pressure curve, it would look like this, meaning that at a given pressure, the very first temperature that's encountered must be nitrogen's, because that's going to be the lowest boiling point, and then we must intersect oxygen's line farther to the right because its boiling point is higher. So oxygen has the stronger interactions. Nitrogen has the weaker interactions due to the placement on the potential energy curve. Okay, so here we have a vapor pressure curve with 3 different substances, and then you're asked to select which ones are correct. At 5 atmospheres and 300 Kelvin, so let's take a look. 500s there, 300s there. So in those conditions, we know we have propane as a gas because we're below the line, but we're in liquid form for isobutane and butane, right? So with the phases, and they have different masses, right? So we got to take that into account because they have different formulas, which we'll get into in detail in Module 3. But we see they have different masses, and they have and propane is in a different phase, a high potential energy phase compared to isobutane and butane. So with this information, we'll go through the answers and say, well, do all particles have the same average speed? No, because they have different masses, so A is wrong. Do they all have the same kinetic energy? Of course they do, because they're at the same temperature. Same average temperature, same average kinetic energy. Under these conditions, propane has more configurations than isobutane. Absolutely. Propane is a gas. Gases always have more configurations than liquids, and so C is the correct answer. Under these conditions, propane has more potential energy. Absolutely. It's a gas, so gases always have higher potential energy than liquids. Butane and isobutane can be separated. Not under these conditions. At 5 atmosphere and 300 Kelvin, they're both liquids, and so they cannot be separated. You can only separate when the substances at the temperature given and pressure are different phases, right? That's how we characterize differences. Okay. In which of the phase present in the chamber do particles have the lowest potential energy? All right, so we just need to identify gases, liquids, and solids. If we look at this picture, we definitely have a liquid. We don't have solid, which would be a regular array of very close particles. So we have a liquid. We have gas up there. Gases have the highest potential energy. Liquids have the lowest, so we would pick liquid. Straightforward. And this is going to be a general analysis for all particles that are closer together than another state. Okay, so what would the potential energy and kinetic energy of CO2, how would they change as we're going from A to B? So from A to B, there's no change in temperature, so there's no change in kinetic energy. That means the only two possible answers look like A and B. And now we have to know what's the change in phase. The change in phase is going from high potential energy gas to low potential energy gas. Going from high to low, potential energy is decreasing. So that would give us this answer, right? So knowing temperature does not change means kinetic energy doesn't change. And knowing that the potential energy is going from high to low means it's decreasing potential energy. Here we have a phase diagram, and it asks which graph best represents the change in total energy versus temperature as N2O goes from point A to point B. Well, so point A, so we put in the phases, and we see that point A is a gas. It's at around 310 Kelvin and about 10 atmospheres. B, on the other hand, is 200 Kelvin, same pressure. And so we're definitely going from gas to liquid. We got a change in potential energy and kinetic energy. So we would expect, so high temperature, low temperature. So the only two possible graphs we have are B and C because we're starting at high temperature. And so temperature so delta E at 0 has to be at a high temperature. A and B both have starting temperatures at low temperatures. So delta E equals 0 is the initial temperature, and the initial temperature is high. Then what we have and now what we have is we cool the gas, A goes cooling, then we have condensation, gas to liquid, same temperature, and then we cool the liquid. So the graph most consistent with that is C, cool the liquid, condense the liquid at the boiling point or the condensation point, and then cool the liquid. So we would pick C. C is the correct answer given what we see happening. B is never going to be true. You never have a change in temperature when delta E remains constant. So here we have a phase diagram, and the question asks, what pressure do we need to have on the y-axis to assure the liquid phase? So we put in the solid liquid phase, solid liquid gas, right? This is our, so we're looking at the blue region. At 162, we have to cross from the brownish region into blue. And this is going to happen above 1 ATM at minus 162. So 10 ATM is a good answer. B is not a good answer. That's 10 to the minus 2. That would give us a gas. And 10 to the 4, that's way too far. We'll leave the liquid region. We would leave the liquid region, and we wouldn't have a liquid. We'd have a solid. So the best answer here is C. And that's never a good answer, not enough information. All right, so now we're going to we're going to graph again some delta E total versus temperature for going from A to B. And then we'll do the same thing with the change in kinetic energy versus temperature and change in potential energy versus temperature. All right, so going from A to B is going from a solid to a liquid to a gas. So we want to put the temperatures, right, so of the phase change. So 1, 2, 3, 4, and 5. So there's 1, heating the solid, 2, melting the solid, 3, heating the liquid, 4, boiling the liquid, and 5, heating the gas. So it would look something like this. Melting the solid, 3 is heating the liquid, 4 is boiling the liquid, and 5 is heating the gas. So this was the graph we made in Unit 1, Module 1, and now we've talked about kinetic energy and potential energy, so let's just take a look at each of the regions. In Region 1, we're heating the solid. There's no phase change, so potential energy does not change. We're heating the solid. Temperature's changing in Region 1, and so the answer is yes. Kinetic energy changes, and it's plus. 2 is a phase change, and potential energy increases as we go from solid to liquid, so the answer is yes. And 2, no change in kinetic energy in the phase change of melting, so that's a no. 3, heating the liquid, no change in PE, in potential energy, but yes, a change in kinetic because we're changing the temperature of the liquid. Region 4, we're boiling. Yes, going from liquid to gas is an increase in potential energy. Kinetic energy, that's a no, because we are not changing temperature in the phase change. 5, the answer is yes. Nope, the 5, we're only heating the gas, so the answer is no. That's a good test. Kinetic energy, yes, because our temperature of our gas is increasing. So all the places where temperature increases, kinetic energy changes. All the places where there's phase change, potential energy increases. So here we have a change in kinetic energy with temperature, and that's just a straight line. Anytime temperature changes, potential energy changes, or kinetic energy changes. Potential energy is very responsive to phase changes, so we have a step up. So there's no change heating the solid, a small step going solid to liquid. Then we go over and the liquid to gas boiling. There's a big step, and there's no change in potential energy heating the gas. All right, so the sum of total energy versus temperature is a sum of both of them, and that would be the curve on the top. It's really important to feel comfortable with all these individual changes. Phase change. And here, temperature changes, kinetic energy changes. All right, so here we have a mixture, and we're going to answer some questions about this mixture. How many phases are present? Well, it looks like there's a liquid phase and a gas phase. We would say 2. In which phases are the particles moving at a higher speed? Well, it looks like the gas phase are smaller molecules, less atoms, so we would say they probably have less mass and are moving faster. So we would pick the gas as moving faster, the liquid is moving slower because their particles are bigger and heavier. Which phase do particles have the lowest potential energy? Well, that just means which phase is closer. That's definitely got to be the liquid. And in which phase do particles have the highest kinetic energy? Well, we know that if they're all at the same average temperature, then they have the same average kinetic energy. So that's how we would answer those particular questions. All right, so here we have a PEC diagram that we need to draw. We're given some information about fracking and about gases that are trapped in rocks, constricted versus free gas particles. All right, so we're going to analyze this by looking at a picture. So here's the trapped gas in the rocks. And then we have the rocks down, and here for the free gas, and so the gases are really far apart now in the free case. So if that's the case, the potential energy is higher for the released gas because they're really, really far apart, while the potential energy for the trapped gas is really low compared to that because the gas particles are forced to be close to each other because of the trapped nature of the system. Since they're constrained to be near each other, the configurations is lower because there's a constraint. While the free gas doesn't have any constraints, so it has the highest configurations. So with that, we can name our states free and released and trapped, and now we can assign the potential energy and configurations. So we do that. At high potential energy and high configurations, we have the MR state, the methane released state. And then at low potential energy and low configurations, because it's constrained in the rock, we have the MT state. That means that at low temperatures and high pressures, we would expect the methane to remain trapped. At high temperatures and low pressures, we'd expect the methane to be released. Right, so here we have some boiling points, and now we need to draw the vapor pressure curve. So 3 different temperatures, and so we would draw it like this. We know we have 3 substances, so we draw a line at a given pressure, and wherever it intersects is the boiling point. And so we drop down here, so T boiling, and T boiling. We convert the temperatures to Kelvin just to make it a little bit easier. The 110 is the lowest boiling point, 230 the highest boiling point. That means the lowest boiling point, which is the farthest to the left, lowest temperature, must be methane, then ethane, and then propane. Right? So the lowest boiling point, methane, is always drawn to the far left, right, up and to the left. And the lowest boiling point is always going to be to the far right as you go farther in temperature on the x-axis. Okay, so you need to be prepared for drawing the vapor pressure curve and using it to extract information. What kind of information are we going to have to extract? Well, we could answer questions like this. So based on the boiling point, we can put all the gases up near zero, because gases have high potential energy near zero. We have 3 different boiling points, so we must have 3 different potential energies of the liquid. So the most unstable liquid, which has the lowest boiling point, and the most stable liquid, which has the highest boiling point, can now be determined. So methane has the highest potential energy, weakest interactions, and propane has the lowest potential energy and the strongest interaction. So which one's more volatile? The one with the lowest interaction, lowest strength interactions, lowest boiling point, and that would be methane. Which substances have the stronger interactions? Well, that must be the lowest potential energy. And which substance have a higher potential energy in the liquid phase? Well, that's definitely methane, right? So just keep in mind that the potential energy, that stability of the liquid, goes opposite of potential energy of the liquid. So the lower the potential energy of the liquid, the more stable the liquid is, and the stronger its interactions. Weakest interactions are with methane, strongest interactions with propane. Okay. So in this question, we're given, and methane requires 10 atmospheres at minus 162 to liquefy, but hydrogen remains a gas. at 10 atmospheres and minus 162. So that's the information given here, that the under the condition specified, hydrogen exists as a gas. So if that's true, hydrogen is a less stable liquid than methane. Methane is a liquid under these conditions. Hydrogen is still a gas. So if we were to rank the potential energy of the liquids of methane and hydrogen, it would look like that. So we know that hydrogen's liquid is less stable, higher potential energy than CH4 is as a liquid. All right, well, so we look at these PEC diagrams that are given, and we can see right away that C and D are wrong. Gases, which are shown with that far spacing, are never going to have lower potential energy than the liquid, so those are definitely wrong. So the choice is between A and B. Well, we know hydrogen's potential energy as a liquid is much higher, less stable than methane, and so our answer would be B. B is the right representation that hydrogen is a gas, while methane is a liquid under specific conditions. All right, so our final slide is about, so we're given a system, chlorine dissolved in water and chlorine undissolved in water, and the question is, under what conditions do we expect to dissolve Cl2? Which one is it favored in? So first we make the diagram, and so the diagram is constructed because A has low potential energy, because the particles on average are closer together and they're constrained, so they have lower configurations. B, the undissolved chlorine has higher potential energy and high configuration since there's a gas present. So using this information, we'd expect A to be the low potential energy, low configurations, and B to be the high potential energy, high configurations. So if A is the dissolved state, we'd expect to meet that with low temperatures and high pressures, which the answer would be B for question 6. Okay, so if you feel comfortable with the questions that were in this activity, then you should feel very prepared answering the questions on Unit 1, Module 2.